2.7 question is whether or not the cost to attend college has been growing linearly or exponentially. We'll take a quick look at the data here back in 1981. The average cost of college tuition was $2,663. Now notice what this data includes. So first we've got average tuition costs, meaning we added up all public American colleges and universities. So that includes 2-year and 4-year institutions, public only, not private. Private's significantly more expensive. And so we add them all together, divided by how many, that's our average cost. So there will be some colleges that charge more, some that charge less, etc. The other thing to note, I did look this up where this information came from and found that this average tuition costs was for 1 year of college, and it included room and board, fees, and tuition, which I think, as best I understand, that excludes the cost of materials, so textbook stuff, other things. So this is living on campus in a room, all the student association fees and student activities fees that get charged, internet access fees, whatever, plus the cost to take the class. So notice back in 1981 we were at $2,000. In 2011 we were at $14,000. What is it today, right? We're going to look that up shortly. So the first thing we want to do is get a picture of that. But to do that, we don't like graphing these really large x values for a couple reasons. Number one, if we were to graph 1981, if this was 0, then we're at 1,981 in terms of our very first x value. And we really want this to be our starting x value. We want this to be our initial value. If it wasn't, then our initial value is like AD, like year 0, which maybe there was probably universities back then, but I don't think there was American universities that we know of. Who knows? So what we do is we rewrite all of these years in terms of years since 1981, because this is our starting value. So 1981 would be 0, 91 would be 10, 2001 would be 20, and then, ooh, look at that, it changes. This would be 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. That's what we're to put on the next page. If you want a tried and true method to calculate this, we already did this in 2.5, but in case you're forgetting, you take, to find the x value, you take the year you're at, so 2011, and you subtract from it the year that we started with, and that gets you the x value that we're going to use, where this represents years since 1981. So we would have filled this in on the previous page, but why bother? What we really want is to get a graph of this in Desmos. Now, I don't want to do this mess, right? I'm not going to do a great job. It was 0 in 2000 something. I mean, I have to fill in these scales and all that mess. So, in my opinion, always go to your technology to get the pictures. So let's do it. Just as a reminder, what we want to do here is enter a table of values. So we hit the plus sign, click table. Notice x1, y1 is what this starts with. And then we're going to type in our numbers, 0, 10, 20, but we don't want 30, 21, 22, 23, 24. Oh. Okay, so I took a moment to enter the values, took a little bit, since I don't have a number pad on my school supply laptop. But here's the list. It's pretty big. You're going to have a similar situation, and unfortunately Desmos does not have a nice way to copy and paste values into it. You just have to manually type it. Be very careful, double check your work, make sure it's accurate. So we can't see the graph, and as usual we find this zoom fit button, and there's our data. So you can see these big 10-year gaps here between the first 3 data values, and then a pretty steady looking rise. So I think if we were just looking at this, I would think that looks like a linear relationship. But if we include these values, it has a sense of a curve like the exponential. So it's tough to tell, right? It's pretty close. So our first question that our author asks us is, based on your scatter plot, which type of equation do we think would be most appropriate? Linear, exponential? Explain your answer, please. Boy, I'm going to say linear if we ignore the early values, exponential for all values, but either way, tough to tell. So we've got to have a better way. Well, you know the better way. That is the finding a model and looking at the R values. So we're going to go ahead and find a linear model first. We call we type y1 tilde mx1 plus b, and there's our linear model. Notice I'm using x1 and y1 because that's what's in the table. So our author said to use 5 digits total. That gives us y equals 385.66x plus 1501.2. 1, 2, 3, 4, 5. Yeah, so there is our linear model. And we've graphed it on the screen. How well did that fit? That's not great, right? It hits these 2 points quite well, but it misses this curve, and there does seem to be a departure from the adding of a constant. So let's just say not great. But to be able to tell how well that actually models the value, what we want is the correlation coefficient. Remember, that's the R value. So let's grab that R value. Hey, it's 0.9709. I believe this is the lesson check, y'all, for 2.7. You'll have to correct me if I'm wrong, and it says rounded 2 decimal places, so that'd be 0.97 for the lesson check. So I've got that written down here. I believe 2.7 lesson check. So does this change our perspective? Oh, definitely. This is a fairly strong correlation, is what we'd say here. And that's because R is close to 1. Remember, the closer to 1 we get, the better the fit. You can ignore all this if your calculator is not displaying that junk. We're using decimals. It just tosses it in there for us. Okay, so this tells us it's not bad. It didn't look great, but it models it quite well. So let's make sure we can identify what the slope is and write a sentence in context explaining that. So I'm going to rewrite my equation just so I have it here. It's 385.66x plus 1501.2. Remember, the slope is the number times x. So also recall that our definition of slope is change in x over change in y. Well, in words, the change in y is change in tuition, and x, boy, can I not spell tuition? We'll pretend like that's spelled right. And x is just change in years since 1981. So if we keep that in mind, I think it becomes fairly straightforward as to what this slope is. I'm now going to replace the words with the numbers. So this would be dollars. That's what our measurement of that. And this is per 1 year. So a sentence would say, tuition. Boy, I definitely spelled that wrong. Here's how you spell tuition. Tuition has increased by, we'll say, about $385.66 per year since 1981. We say increase because it's a positive number. If it had been a negative number, we'd say decrease. That obviously does not happen. There's billions of dollars in student debt. It's actually quite a big problem. Okay, so that's what's going on there. Let's just for fun interpret the y-intercept, because that's something I ask you to do in the project. Remember, the project says interpret the parameters. So for the linear equation, these are the 2 parameters. So the y-intercept, in this case, is 0 comma this value, and what it claims is that in 1981, the cost of tuition was 1501.20. Definitely different than the actual value, quite a bit different. That's okay. This is a model. Notice we said it was 2663 is the actual value. But once we got our model, we're wanting to interpret what does our model tell us about the